The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
My name is Thomas Mander. I do consulting for Baker Risk, and I'm also doing a PhD at the University of Texas at San Antonio. This presentation I'm going to be giving today is it ties in well with what Marlon spoke about and also what Matt spoke about. Now we're actually going to look at load-bearing panels. So this is a program that was funded by PCI between 2014 and 2016. It was a large research program that involved a lot of testing and analysis. The outline of the presentation, first really the research significance. Why did PCI want to do this research? As part of that research, we did a lot of shock tube testing and modeling using finite element and single degree of freedom models. I'll be covering some of the single degree of freedom modeling today. And then really the meat of the subject, what we want is some response criteria that we can actually use for analysis and design so that load-bearing panels can be used safely in environments where you have blast threats. So significance. Load-bearing panels really haven't been researched all that much for blast applications. What that means is that people are usually hesitant to design using them, or when they do design using load-bearing panels, potentially they could be designing them in an unsafe way. So we need a set of response criteria that people can design to, and that's what this research program accomplished. So we had a number of full-scale tests, and from that we developed a single degree of freedom methodology and then fit response limits to that methodology. If I'd known the student competition was going to be behind us, I probably just would have shown videos the entire time to drown out their noise, but there's a couple videos here. So this is a non-load bearing panel tested successfully in a shock tube, and really that's a good panel performance. That's what you want, and what you want to try and prevent is from this happening. And this is a load bearing panel that's tested, and you'll see it responds and then it fails catastrophically due to P-delta effects. Again, all you, I'm sure, have memorized this table now because it's been shown so many times. But the main thing that I want to point out is this row that's highlighted here in yellow. So these are the existing response limits that are used typically for architectural panels. Very low limits, and one of the problems with this table is that this is only for non-load bearing members. In contrast, the bottom table here, this is for reinforced concrete response limits, and you can see the thresholds are much higher, so heavy damage 1.5 compared to 5. But the other thing to note is that for reinforced concrete, there is flexure compression response limits. Now these are a little bit, I guess, simplified on top of how simplified these tables already are, but essentially what's done is the moderate damage level is used for limiting how much response you can let a member go through when you have a member that's both in flexure, so out of plane, and then also in compression, so carrying an axial load. Moving on to the shock tube testing, I'll give you a little bit of a rundown as to how we did the actual testing. Right now what's seen here is the Baker Risk shock tube. So the way that we apply a shock load onto a specimen at the end of the shock tube is we generate pressures inside this driver region here, and this volume can change depending on the duration that we want to get out of the blast. And then we've got that separated here by some ruptured diaphragms. Those diaphragms will fail, sending the shock wave to travel down this expansion section and load what's ever at the end of the shock tube. So this kind of gives you a video as to how it's happening. The end here is our expansion section. So that's 16 feet tall and 10 feet wide. So we narrowed it down so that we could have more manageable specimens. So we have 4 foot wide specimens that are going to pop up here between there. At the top right now, what we're looking at is a load bearing apparatus. This is something that we designed. It's kind of the first of its nature. The way that it works is a series of airbags, and we pressurize those prior to the test, apply an axial load on top of the wall. So that's the wall there in place now. And then that axial load is essentially maintained throughout the entire test. So even as the panel's deflecting and it's starting to shorten, or as it even wants to elongate, you are maintaining that axial load throughout the test. And this is what it looks like in the shock tube. So again, 4-foot wide specimens is what we're testing, 16 feet tall. And then you can see at the top here the large load-bearing apparatus. One thing I want to touch on is the axial load magnitude. The table that I previously showed for the reinforced concrete response limits, really you don't have to start taking into account compression effects until you get to 20% of your gross axial capacity. That's an extremely high number, something that I think needs to be brought down a lot, and it's very unconservative, particularly for architectural panels that we're looking at. Just because usually you have a low moment capacity, and this value is going to kill your panel in P-delta effects. So in this test program, what we did was we reduced the amount of axial load that you're allowed to put on a panel before you need to start considering the effects of axial load. So those thresholds were 5% and 10% of the gross axial capacity. And in this particular test program, this was based on a nominal compression strength of 5,000 psi. So just for give you an idea, for this 10%, we had a 6-inch thick panel that we were testing, 4 foot wide. The axial load that we were applying was 144,000 pounds throughout the entire test. So it's a very large axial load. These two values as well are understood to capture the majority of load-bearing walls that you would come across in industry. The research program in entirety looked at solid panels and then also sandwich panels. So panels that had 100% and panels that had 60% composite action by design. What I'm going to focus on today is just the solid panels, just because of time. So these are the panels that we tested. We did, I think, 5 or 6 of these same specimens. They were 6 inches thick, and they had concentric pre-stressing, and the initial pre-stressing ratio is around 250 psi. This is jumping straight into the results. So there's 2 different charts here. We'll start with the one on the left. So we also tested some non-load-bearing configurations as well. What's shown here, each of these bars represent an individual test that was performed. Colors also represent the qualitative damage that we observed. So for example, green is superficial, M moderate, H heavy, and then B blowout, where we have complete failure of the panel. What you'll see here is on the right-hand side, we move into load-bearing, we classify things in the same way, but all of those values at which we start to see certain levels of damage, those decrease as you would expect. What's shown here on the load-bearing graph, we have the hatched plots that are for the 5% axial load and then the solid for the 10%. So we've plotted everything on the same charts. The blast loads that we were testing range from between 4 to 7 psi. So these are more typical of what you're going to get in industry, people that are designing against vapor cloud explosions, and then the durations are around 40 milliseconds. What else? The other thing that's important to note on the slide is that when we plot horizontal lines of the current response limits that people are designing to, you can see that these panels are certainly outperforming those limits. So for example, if we just focus here on the moderate level of damage for this non-load bearing panel, this could be the upper threshold, but albeit at 3 degrees support rotation, that's much higher than what you're currently allowed to do at around 1 degree support rotation. So those limits are overly conservative. Likewise, when you move into the load bearing, we're actually outperforming the non-load bearing criteria for this particular set of panels. And that's what's important to emphasize, is for these panels. This doesn't necessarily apply across the board, as Matt mentioned, and I'll also talk about that a little bit more too. But the big takeaway is that we actually are getting decent performance out of load-bearing panels, even with panels with a high degree of axial load on them. Moving into modeling, really what you're doing when you're solving or calculating what kind of damage you're going to have to a blast-loaded component, in most cases you're going to be using a single degree of freedom method. So you're solving the equation of motion, and what you really ultimately need is the Kx, and then this becomes it's really a nonlinear term rather than just Kx. And that's your resistance function down here. So the graph on the far left, the way things are done right now is very simple. It's an elastic, perfectly plastic resistance function. So if you open up SBEDs, or if you were to make your own single degree of freedom model, that's usually the resistance function you're going to use. And then you've got your forcing function. This is an actual pressure trace from one of our tests. And that's your input there. And then ultimately what you want to calculate is what your displacement is, okay? And from that displacement, you're picking out your peak transient displacement that you get in your response and converting that into an equivalent support rotation, and then comparing that support rotation back to published criteria. Now, these simplified resistance functions are obviously very nice to use when you're coding things in a spreadsheet or even in, say, MATLAB. One of the downfalls with them is they don't really give you any indication as to what is happening to the panel itself. So you've got this really wide ultimate resistance up here, and this doesn't give you any indication as to how much damage your panel is actually incurring throughout the response. When you move to something like a moment curvature, and this is similar to what Matt and the people at Lehigh have worked on, you can actually start quantifying when different damage starts to occur. So now with this black curve here, this is a moment curvature, and we can start to pick out some points of interest that actually have some meaning to the materials that you're using. So for example here, this gray spot is going to be cracking, and then we've got the proportional limit for steel, and then some other points here, so pre-stressing at yield, reaching your peak concrete strength, and then here where you're going to have concrete at a strain of 0.003, and then you start to lose strength, and then ultimately you get to your ultimate moment. Okay, now the other thing with axial load is that everyone was taught in school that when you apply an axial load onto a member, you're making your member stronger, and that's usually shown in an interaction diagram, provided you're below the balance point. The problem with this is it really doesn't give you any kind of indication as to what's happening to the ductility of the system itself. So when we use those same moment curvature plots and then convert those into moment displacement, what you see is, of course, an increase in strength, but more importantly is you have this reduction in ductility. And that's a huge thing in blast. Really, ductility is more important than strength, because you're really never certain as to what your blast load's going to be, and you want some redundancy. Now, if you're going to compound that by including P delta effects, and this is ultimately what your resistance functions look like. So you actually end up decreasing your capacity and then also decreasing your ductility. And this is why I previously mentioned that the problem with that 20% threshold is just way too high. I mean, this is right now for, you can see 5% in orange and 10% of axial load, and the P delta effect is really significant on these panels. And that's just because the panels usually have a very low moment capacity to begin with. These are the actual resistance functions for that panel that I'd previously shown. We've got some comparisons here between the elastic perfectly plastic and the moment curvature. Again, when you're not accurately predicting what the strength is here in these lower ranges of support rotation, so between around 0.5 degree and 3 degree for this particular panel, you're really over-predicting what your resistance is if you use your traditional elastic plastic response. And that's a problem. It's unconservative. And then this is the same type of plot for 10% axial load. These graphs are basically just to show that we've done some validation. So this includes both the solid panels and then the 100% composite and 60% composite. I'm not covering in this presentation, but it just is to give you an idea as to how accurate our analytical models are using these modified resistance functions in single degree of freedom. The vertical axis on both of these graphs is the predicted support rotation divided by the experimental support rotation. Anything over a factor of 1 is going to be conservative. Anything below a factor of 1 is unconservative. So you can see that on either end of that, we're within about 15% of what the actual response was. So it's a fairly good prediction. What's more important and gives you better validation as to how robust your analytical model is if you can use it to predict what the response is for a member, not once, but multiple times. So 2 blast loads, 3 blast loads, so forth. And that's what we have here. So on the right-hand side, we ran a total of about 30 tests, and we tested some panels multiple times to quantify what the damage was throughout the response. And our analytical model still produced the same kind of results within 15% accuracy on either side. So now using those analytical models and the shock tube test data, what we want to do is come up with a response criteria. But again, Matt pointed it out in his presentation earlier, the response criteria needs to be tied to the individual panels. You cannot just put a set of response criteria based on what you see in one test program, because that could be specific to that member that you tested. So what we did was we ran a parametric study, and we did a range of pre-stressing indices that are typical of architectural panels. And then we also varied the span to depth ratio, which is another important thing in the response. This slide is a little bit involved, so I'll go through it, take a little bit of time to go through it. On the top left-hand side here, we're comparing moment curvature with the elastic perfectly plastic response. Again, when we're using the moment curvature, we can actually pick out points of interest to us on our resistance curve. So for example, what we're doing here is saying at pre-stressing is at yield, what is the support rotation? So there, the support rotation is about 2.8 degrees. Now, if someone was to use an elastic perfectly plastic response or resistance function, which is what people in industry are naturally going to want to do, we're not going to try and force them to use a moment curvature response. You need to provide response limits that are applicable to that particular analysis methodology. So what that means is that if we preserve strain energy, we actually need to dial back what that response limit threshold is so that it's directly applicable to using an elastic perfectly plastic response. So we're preserving strain energy to set the response limits. So we're determining damage states from our moment curvature and then converting those into equivalent damage states using elastic perfectly plastic resistance function by preserving strain energy. And this, I'll go over quickly, the component consequence. These are qualitative limits that are given in PDC, and these apply to irrespective of what kind of member you have, whether it's steel, concrete, wood, so forth. What we want to do is give something that's actually more specific to these panels themselves. Okay, so at a moderate level of damage, for example, we're saying that the pre-stressing has to be at or below yield because, and this is something that maybe a lot of people don't agree on, but in moderate, you're usually telling people that something can be generally repairable. Generally repairable for a concrete building means you need to have some kind of minimal permanent displacement, and that's something else we've also limited to a permanent displacement of L over 360. If something has a permanent displacement of 4 degrees after an actual explosion event, I wouldn't call that generally repairable. How are you going to straighten up a panel that's deflected that much? So we want to actually make this kind of a little bit restrictive. Now these curves are actually similar to what Marlon had in his, where we have a range of pre-stressing indices on our horizontal axis, and then we've got the different curves for our different span to support ratios. So we calculated these top two. The graph on the left-hand side is for 5% axial load, graph on the right is for 10% axial load. And we calculate, this is particularly for superficial damage, we're calculating it when the pre-stressing is hitting the proportional limit. Okay? And what that is showing us is that when the pre-stressing is hitting the proportional limit is dependent on both those things, the pre-stressing indice and then also the span to depth ratio. Because the way the response limits are currently written and we want to keep them fairly simple, what we're doing is fitting a straight line to those. So that's 1 degree is what we're setting as our superficial damage state so that it can be used similar to how things are done right now. If we started introducing complicated equations for people to work out how much support rotation they can actually have, people most likely wouldn't really want to design with these types of panels. And likewise, this is showing moderate damage that we've set with the peak concrete stress. So when your concrete's at around 0.002 strain, and we set a value of 1.5 degrees to that. And then likewise for heavy, and that was based on essentially concrete getting to crushing point. And then the final thing is the amounts that we can actually displace the panel based on P delta effects. So with P delta, and we saw that, we really want to make sure that our panels are not getting to below 80% of their resistance. So we've introduced this empirical equation here, which comes into the response criteria as a ductility term. And that could potentially restrict how far a panel can be pushed. Ultimately, this is the response limits that we came up with. So 1.5 degrees at moderate, 2 degrees at heavy, and likewise hazardous is 2 degrees. And if we compare these back to the existing non-load bearing criteria, we're actually allowing people to go a little bit further than the load bearing criteria. The importance of this is that if people have already been designing panels for load bearing without using a set of criteria or using the existing non-load bearing criteria, those panels could potentially actually be okay. So just conclusions, we tested a number of panels that achieved support rotations in excess of the non-load bearing limits. The moment curvature model that we used accurately predicted what these displacements were going to be, and then using that model, we were able to develop a set of response limits that can be used for design by using traditional elastic plastic resistance functions. These are some acknowledgments. We had a good advisory committee that was made up of people from academia and industry, and then also both of Course Lab and then Tyndall Corporation, who fabricated specimens for us. That's the presentation, if there's any questions.
So it makes sense what you're doing with the strain energy. You're just reducing the response limit based on the quasi-static response of the panel.
Yes.
Did you consider, I mean, what about the other parts of the equation of motion, the damping, the inertial aspect? I mean, it's clearly conservative.
Yep. So damping we neglected. The inertial term, we actually did something similar to what Matt had with KLM factors. We determined what those KLM factors were as well, based on the actual display shape. So we weren't only just changing the resistance, that's really what I showed here, but we were also changing KLM.